since doing the last video about the ordered field properties that we can deduce from the ordered field axioms, I've been really intrigued by the proof that we did for part E of the field properties to prove that 0 is less than y implies 0 is less than 1 over y. So I just want to make this video here to explore this a little more because I find it very interesting that Rudin did this proof in such an odd way and a very unusual way of doing a proof. So I don't really have anything planned here. I just wanted to explore this for a few minutes. So I thought I would just videotape it and then you're welcome to watch it if you want. So part 1 of property E. E was that if 0 is less than x is less than y, then 0 is less than 1 over y is less than 1 over x. And then I said that we are really proving 3 independent inequalities here. First, that 0 is less than x, that 0 is less than y, and then that x is less than y. And the first one was that if 0 is less than y, that if those are true, then that implies that 0 is less than 1 over y, 0 is less than 1 over x, and 1 over y is less than 1 over x. And that, so first that 0 is less than y implies that 0 is less than 1 over y. And to prove this, I followed the way that Walter Rudin did it in his book, which, if you remember from that video, was very odd. It said that if we start with assuming that y is greater than 0, which is what we're given, and then take some number, v less than or equal to 0. So v can be any number. We're just picking a number that's less than 0. If we assume those two things, then we know that yv is less than or equal to 0. And the reason this is true is that if v is less than 0, then if we have that y is greater than 0, then if we multiply both sides by something that's less than 0, then we have that yv is less than 0v, which equals 0. This is part C of the ordered field properties. That if you multiply both sides of an inequality by a number less than 0, then it changes the inequality. So we did all this, and this is all fine. And then, of course, if v equals 0, then if you just multiply it by 0, you're going to get 0. That part's easy. So if v is less than 0, then it flips the inequality, and yv is less than 0 if y is greater than 0 and v is less than 0. Okay. So we have this. Then the next step of the proof is to remind us that we already know that 1 times 1 over y is 1. And we just proved in the last section one of the other properties is that 1 is greater than 0. We proved that. So we know that 1 times 1 over y is greater than 0. And then Rudin concludes, he actually says, hence, 1 over y is greater than 0. Now, I showed why this is true in the last video, that he basically, what he's doing is he's starting with an assumption. He shows the conclusion of that, and then he says, but if the conclusion is not true, then the assumptions must not be true. That's the contrapositive. So I showed in the last video why all that's true. But this is all, it's a very odd way of doing it to me. And so I was wondering, I keep thinking about whether we can't just do this, doing it the normal, assuming something and then assuming the opposite and then proving a contradiction. which I think we can. So I wanted to try that here and see if we can't do this in a way that's a little less odd and seemingly out of the blue than this. So if we assume that y is greater than 0, that's what we're starting with. That's the given. Now, we need to show that 1 over y is greater than 0. Okay, standard way of doing that, let's assume the opposite. So if y is not greater than 0, that means it's either less than 0 or 1 over y is either, if it's not greater than 0, it's either less than 0 or equal to 0. So let's assume that 1 over y is less than or equal to 0. Now, it's clear that it's easy to see that it's not, in fact, 0, because if then y times 0 would have to be 0, not 1. So y can't be 0. So really, we're just looking at 1 over y is less than 0. So let's assume that 1 over y is less than 0. So we already know, as we said above, that if you multiply, so we have y is greater than 0, and we're assuming that 1 over y is less than 0. If we multiply both sides by a negative number, it flips the sign. So that would mean that 1 times 1 over y is less than 0 times 1 over y, which equals 0. So if we assume that 1 over y is less than 0, then we have that 1 times 1 over y is less than 0. But we know that y times 1 over y equals 1, and that 1 is greater than 0. We've already shown that. So this is a contradiction. If 1 over y is less than 0, then y times 1 over y is less than 0. But we know that 1 times 1 over y equals 1, which is greater than 0. That's a contradiction. So this assumption must be wrong. Therefore, 1 over y is greater than 0, which is what we wanted to prove. That seems perfectly legitimate to me. Unless someone can find something wrong with that, this seems like a much more straightforward proof of this statement than what Rudin did. The question is, why did Rudin do it this way? And I can't see why readily. The only thing I can think of is that it's a stylistic thing, not a logical thing. That when we assume the opposite and reach a contradiction, we start with some assumptions and then go through some logical steps and end up contradicting the assumptions. And actually what we did here, we didn't actually contradict the assumptions. What we did is contradict something else that we know. We already know that y times 1 over y is 1. Whereas by our assumptions, y times 1 over y is less than 0. So maybe there's some very subtle technical point here stylistically that this isn't actually reaching a conclusion, or I'm sorry, this isn't actually reaching a contradiction because we're not contradicting an assumption, we're simply contradicting something else that we know. So that may be why he did it the way that he did it, because it's not exactly assuming the opposite and then reaching a contradiction. It's actually assuming the opposite and then reaching something that doesn't work. So it's practically the same thing, but maybe stylistically it's a tiny bit different, which is what led him to do this. We'll have to keep an eye on this as we go forward, see if something like this comes up again. Okay, so while we're here, there's one last thing that I wanted to look at. There's this rule that if x is greater than 0, then the inverse of x is less than 0 and vice versa is very similar to the one we've been looking at, that if x is less than y, then 1 over y is less than x. And I just wanted to look at that a little more, because we haven't really talked about that very much. There's a deep similarity between the addition axioms of a field and the multiplication axioms of a field. And as I've said before, they're both groups. Fields are an axiom. Fields are a group under addition and a group under multiplication, with one exception, which is that 0 does not have a multiplicative inverse, because there is nothing times 0 that will equal 1. Never, right? 2 times 1 over 2 equals 1. Everything else has a multiplicative inverse except 0. That's the only reason that it's not a group. So the additive inverse says that x plus the inverse of x equals 0. The multiplicative says that x times x, the inverse of x, equals 1. And again, that's true for everything except 0. So what's interesting is this rule says basically that all inverses are on opposite sides of 0. They don't have to be. 0 could be at one end of the numbers, but it's in some sense in the middle of the numbers, that if one number's on one side, then the inverse is going to be on the other side, and then they come together to 0. And this doesn't mention the inverse, but it is, I think, clearly true from this that if you have one number that is greater than 1, then its inverse will be less than 1. So I think that's kind of, if you think about it a second, it's easy to see. 2 is greater than 1. It implies that 1/2 is less than 1, right? And vice versa, 1/2 is less than 1 implies that 1 over half equals 2 is greater than 1. And so it's interesting to me that proving this was so convoluted when proving this was so easy, and that this actually doesn't mention, it's not actually exactly the same rule, but it's kind of there in some way. So I was wondering, first of all, if we can we prove a similar rule to A about multiplication? And if not, why not? Where does it fall apart? So let's just go through it. So if we start with, we have x is greater than 1. That's this. And then we multiply both sides by the inverse. So we have 1 over x times x is greater than 1 over x times the multiplicative identity. That means that this side is 1. I'm sorry, this side is 1 over x. And this side is 1. So if this is bigger than this, then that's less than that. Therefore, 1 over x is less than 1. So it looks the same. What's missing here? That seems straightforward. The problem is in multiplication and inequalities. Because remember, the rule for axiom 2 of inequalities says that x plus y is greater than 0. Oh wait, is that the one that I want? Well, yes and no. The issue is actually, it says that x and y is greater than 0 if x is greater than 0. If x is greater than 0, y is greater than 0. Right? In other words, two positive numbers are always greater, multiplied together are always greater than 0. But then the other issue is that if a number is greater than 0, then it preserves the inequality. But if a number is less than 0, then it reverses the inequality. So the problem here is that with multiplication, multiplication isn't as straightforward in an ordered field as addition. Because with addition, if you have an inequality and you add the same number to both sides, I changed the letters there, but it's the same thing. You add the same letter to both sides, and it doesn't matter. Z can be minus, one of these can be minus, they both can be minus, they all three can be minus, it doesn't matter. Addition doesn't, whoops, addition doesn't change the inequality, even though I wrote it that way. So, but with multiplication, if you have that y is less than z, and you multiply both sides by, say, -2, then -2y is going to be greater than -2z. Because when you multiply by a negative number, it switches the inequality. So they are similar, but multiplying has this weird, there's this relationship between 0 and 1 that keeps things from being completely symmetric. Because multiplying by negative numbers, so even the concept of negative numbers is a concept related to addition, not multiplication. In fact, that's the issue. That what we're actually saying here, the rule about changing signs, this has to do with addition, not multiplication. As long as x is greater than 0, and what we really mean is that it's greater than or less than 1, then there's no issue here. The issue is simply that negative numbers are like this weird other world when it comes to multiplication. It's fine for addition, but not when it comes to multiplication. And in fact, that's exactly why eventually we're going to need complex numbers. Because multiplication simply doesn't work for negative numbers in this sense. So the problem here is we have never actually said whether 1 over x is positive or negative. But what we haven't shown is which is this. If x is negative, is 1 over x negative or positive? We don't know. And it's obvious, again, this is all obvious from grade school, but if you look at it like this, is that necessarily the same sign as this? It's really, you can't really just state that it's true. We would need to prove it. I think that's the entire reason for the proof being the way that it is, with sort of showing that that if yv is going to be less than 0, if v is less than or equal to 0, and so on. It's because we haven't explicitly shown that this is also positive. So in order to prove this, I think that we could do it, but we would have to prove that that's also positive. So I think that just for simplicity, I think it's just easier to just prove this. And then the other issue is, it's also interesting that they just stated that all of these are positive. But again, we had to prove here that if y is greater than 0, then 1 over y is going to be greater than 0 too. We had to prove that. It's still interesting, the relationship between addition and multiplication, because we have a concept of positive and negative that only has to do with the addition axioms. There is no concept of a number being greater than 1 or less than 1, but there could be. We could define x to the minus 1 as, in some sense, negative, and make all of this exactly true, and it doesn't do anything. Because remember, the ordered field axioms state that that if y is less than z, then x plus y is less than x plus z, and if x is greater than 0, y is greater than 0, then x, y is greater than 0. That's all it stated. And notice that they're not saying the same thing. So we are somehow privileging the positive and negative. We're giving that more of a meaning when it comes to addition than multiplication. And then we have to complicate the multiplication by saying that the multiplication can flip the sign. It's interesting to imagine whether we could define order in a different way using multiplication as the concept of negative and positive and addition to flip the sign. I don't know. But related to this, or maybe sort of helping to explain this, is that there's actually an isomorphism between addition and multiplication. And that isomorphism is because we have that x plus minus x equals 0. And we have that x times x to the minus 1 equals 1. So remember, if you're multiplying the same base, then you add the exponents, right? So x times x to the minus 1 equals x to the 1 minus 1 equals x to the 0 equals 1. So basically, if you have the same base, like if we can pick any base. This could be 2. 2 times 2 to the minus 1 equals 2 to the 1 minus 1 equals 2 to the 0 equals 1. Or, more commonly, e to the 1 times e to the minus 1, etc. As long as you have the same base, then you can see that what we've ended up with here is exactly the addition axioms, because e to the x times e to the minus x equals e to the x minus x equals e to the 0 equals 1. So you can rewrite your addition group, or you can rewrite your multiplication group as an addition group. They're isomorphic. This is the same operation as this, right? The thing about this is, though, that each of these numbers is positive. Because if you were to graph e to the x, it looks like this. It never goes negative. So that's interesting. And so the isomorphism between addition and multiplication is not between all of the reals. It's just between the positive reals. So it's interesting to think about. So what if we had the positive reals as our number system, and we considered multiplication to be the addition, and then we added another operation to it that would be multiplication here? What would that look like? I don't know. But the issue is, and this is actually, we're going to get into this when we're proving the uniqueness of the real numbers. we're going to be learning a lot more about the structure of the number system. And because of how integers are defined, they require this sense of a number being greater than 0 or less than 0, and being greater than 1 or less than 1, it just isn't required, again, because of the axioms, the way the axioms are stated. So anyway, all that is very interesting. The other thing that we haven't proven in order to show the isomorphism is that all of these actually exist, because can every number actually be expressed as a root or an exponent of e? It's true, it can be, but we have to show that. So I think that in order to define, to make this proof, in order to make this proof for multiplication, we would also have to show that every number has a root, which actually we're going to show after we show the, we're going to show starting in the next section when we start constructing the real numbers, and we're going to look at some properties of actual real numbers as opposed to fields. So the last thing, one other point I want to mention here is that modular forms are only in the top half plane of complex numbers. So we have I here and R here, and modular forms only deal with complex numbers that are above 0i. So that might very well, I don't know this, but we might end up finding out, that might be very closely related to this. This clearly relates to complex numbers. And there might be a reason why modular forms also don't go below 0. We'll have to find out. So it's all very intriguing. It all gets already so complex with just these simple little rules that we started with. It's very interesting. And again, we're just scratching the surface. And starting next time, we are going to be constructing the real numbers, which is very interesting. And then sort of the crown of this little series of videos is we're going to prove the uniqueness of that set of real numbers, which is something that I cannot find anywhere on the internet, and no videos at all. And the proof is actually quite interesting. In order to prove them, we're going to have to dig into the structure of the natural numbers, the integers, the rational numbers, and then the real numbers. And by going through this proof of the uniqueness of real numbers, I think it actually gives you a much stronger sense of the structure of the real numbers as a whole. Again, it's all things that are obvious without thinking about them. They're less obvious once you start thinking about them, and then you realize, there's a relationship here between the naturals and the integers, and then between the integers and the rationals. And what's amazing, the whole point of the uniqueness proof, is that because of that structure, each element is sort of locked into its place. So there's no room for variety. There's only one set that is an ordered field with the least upper bound property. Okay, again, thank you for listening, and we'll start constructing the real numbers next video. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.